All right. All right. Now, in your notes, in your notes, these are some things that I want to focus on from yesterday. Okay, and I put it up on the side of the board here as well. But these are three ideas or so that really are going to be important when it comes to the parametric equations. Okay, first of all, a parametric equation is x of t equals, and then an equation, and y of t equals. It's two equations, one for the x coordinate, one for the y coordinate, on a graph. Now the graph, we typically talk about the graph of a parametric equation as a path, okay? Especially in the problems that involve motion. So even the unit circle, we can imagine a particle starting at the point 1, 0 on the unit circle, with an angle of 0, and then moving counterclockwise up around the unit circle. And the unit circle would be like the path. Think of it like the sidewalk or the street or whatever. And then the parametric equation describes the movement of something along that street or that sidewalk or that path. Okay? So the graph itself is just a picture of the path, and then the movement on it is determined by where the particle is at a certain time. Okay? So you have your x and your y equation. So if we do the derivative of those, then that would be the velocity horizontally and vertically. In other words, remember, derivative is rate of change. So x prime would be the rate of change of x. Now x is in the horizontal direction. So it describes its horizontal rate of change, which is like saying horizontal velocity. Okay? How much its x position is changing. Its horizontal position. And y prime would be the rate of change of y with respect to t. And that would be the rate that its vertical position is changing, the rate that y is changing. And that's called its vertical velocity. So critically important that you understand that. Probably more above all this stuff when it comes to applications of parametric equations and how derivatives, the calculus aspect of it. Now, we write x prime, y prime, or sometimes we write dx dt, dy dt. Those are interchangeable. I still sense people having difficulty with that notation, and I really can't think of any other way to explain it other than they're the same thing. X prime of t and dx dt are the same. They just are two ways of writing the same thing. Y prime of t, dy dt, they're the same thing. Okay? Horizontal, vertical velocity. Now, think back to the lion problem. All right? And that's what I've got down here in the bottom corner of this. The lion went 0.3 miles every minute to the east, and he went 0.1 miles to the north every minute. Those are speeds, velocities. So that would be x prime, the 0.3. Horizontally, the lion went 0.3 miles horizontally every minute. 0.3 miles per minute. That's x prime for the lion, dx dt. Y prime was his northward change. He went 0.1 north every minute. That's a rate, 0.1 miles per minute. That would be y prime of t for the line. His horizontal and his vertical velocity. Okay? In that worksheet, you had to calculate the rate the line was actually moving, because the line was actually moving on a diagonal, right? Two-dimensional motion. Well, that's an easy Pythagorean theorem. So it makes sense, I'm going to jump to number 3 then, it makes sense that the speed that the line was traveling was this speed, which was x prime squared, plus this speed, which was y prime squared, and then the square root of all that. Pythagorean theorem. Now, we did this calculation yesterday. I'm not sure we did this speed equation. I'm not sure I actually wrote that down on the board yesterday. But hopefully, thinking about the lion problem, that should be sensible to you. So that is going to be an important equation that you're going to have to remember. Okay? The speed of the particle on the path at any given time, this is two-dimensional motion, is made up of both his horizontal speed and his vertical speed. Okay? And this is how it's related. Pythagorean theorem. And again, just go right back to the line problem. This is why the equation looks like that. And we don't even give it a name or a function name. Usually we just call it speed. I mean, sometimes we use S for the variable, but we use that for position a lot. So but we'll just call it speed of the particle. It's in two-dimension motion. Now, we also had a part of the line problem. I think it was the very first problem where you had to write the equation of the line's path, right? And that was 1/3, right? Because that was a slope. Well, the slope of his path, so that's another thing that we're interested in. What's the slope of the path? The slope of the path would be the rise over run, right? Well, that would be 0.1 over 0.3. Well, that would be the y prime over the x prime. This was y prime. This is his rate per minute, and this is his horizontal rate per minute. So we divide those, rise over run. It makes sense that that would be y prime over x prime, or dy dt over dx dt. Now, this one I think I did write on the board yesterday. And it's easy to see that that's dy dx. That's the change in y over x. That's the slope of the path. Change in y over change in x, of course, is slope. Remember, our parametric equation was in x and y. The t was not part of the graph, right? We had miles east was our x-axis and miles north was our y-axis. The difference here is that slope and speed are kind of two different things in parametric equations. You know, when we were back doing derivative problems and we were just doing one-dimensional motion, we talked about slope and rate of change being the same. And so, you know, derivative meant slope meant velocity. I mean, they were kind of all the same thing. But it's two different things here. Because here the slope of the path is dy dx. The speed of the particle has to come from both x prime and y prime that way. So it is two different things. Okay? I hope the line problem can help you to see that, because it's pretty easy to see that the slope here is this divided by this, and it's also pretty easy to see that his speed is how far he traveled in 1 minute. And if he goes 0.3 miles in 1 minute and 0.1 mile in 1 minute, the hypotenuse would be how far he traveled in 1 minute. So, you know, I like that example because it helps to see why it's two different things here. Slope of the path, speed of the particle. All right? I mean, think of it this way. If the path is like this sidewalk, think about adamant and that crazy thing. Let's say you had a bike path or something that looked like that, right? You could have 4 different bicyclists on the path, all going at different speeds. But the slope of the path at any given point is going to be the same, right? The path doesn't change, but you have different particles on the path. They're going to have different speeds. Okay? They're going to have different speeds. So it should make sense in two-dimensional motion that those are not necessarily the same thing. All right. So those have to be pretty much committed to memory. You have to be able to do those things there. So we'll keep those up on the board as we move along. All right. Let's go. Where at? Thank you. You're right. If you copied this off of the board here, that was vertical velocity was dy dt. You may have to start over. All right. Oops. All right. Let's go on to the into your calculator. All right, and try to set your calculator back to the original Windows setting for Adamant, -5 to 5, I think it was. And for the x and negative 2 to 5 for the y. And we were like 0 to 4 pi, I think. 0 to 4 pi was the t range. Now, I think I figured something out on the t step. I think in playing around a little bit, and I apologize for not having played around with that a little more. I made some assumptions about how that was supposed to work, and most of my assumptions on this calculator, based on the way the previous calculators have worked out pretty well. This one seems to be quite different in a couple of things, and so, and I'd be curious if to hear from some of you if you've got some, if you discovered some things as well. All right, but here's the path. Now, one thing I found out that actually has been very helpful is the right click. You can do a right click on your calculator by hitting Control and Menu. Now, the right click doesn't really do anything unless you've selected something first. So if I was to go on here and select this graph, so if you just kind of arrow over it, mouse over it, and then click, and then it kind of starts blinking. All right? Now, if you come over to your on the calculator then and you hit Control Menu, it brings up a little contextual window. And you can go to your window settings. The one I liked was recent. Like if you're tracing or doing some things, and instead of having to go into that menu, I can just come in here to recent. And for example, I can go to Graph Trace. And so now let's say, now mine is going by 0.1 here, it looks like. So let's say I wanted to type in, say, 0.7. Okay, there's 0.7 up here. Oops, darn it. And I keep, try that again. There we go. 0.7 is kind of up there about where that thing goes up in the beginning and then starts to turn around. So there was question number 5, I believe. It was, question number 5 was about when. It was approximately when does it go up and then start to turn around. Now, yesterday I talked about zooming in and stuff like that. Okay, we'll get to that here in a second. In question number 6, they wanted you to see when it comes back down to the x-axis. So if we just keep right arrowing, there's 0.8, 0.9, 1, 1.1. It's coming back down. Seems to come back down here about 1.7. So it wants me to reset my t range from 0 to that. Now, yesterday we had a number of people. Let me see. Let me write on this. We had a number of people telling me on their calculator that when we were going from 0 to, when we were going from, 0 to 4 pi, that's from 0 to about 12 point something. I can't remember, 5.7, something like that. 0 to 4 pi. And the t-step, the t-step would only let us go, what, 0.0, what was it, 0.063? Even though we tried to set it to 0.01, it kept resetting to 0.063. So I took 12.57 and divided it by 0.063, and that came out to right at 200. So evidently what it will let you do is only let you do like 200 t-points that it'll plot. So what it does is it takes that t range that you've done, divides it by 200, and that's the most or the smallest increment you can do. Well, now that we're going to go from 0 to 1.7, that's going to allow us to have a lot more, right? A lot smaller increment because we don't have as big a range. So that's one thing that I figured out on, or that just by trial and error that kind of worked. So if I come back into my window settings and I go 0 and 1.7, oh, whoops, that's wrong. That's wrong. What did I want to do? I wanted to change the t. So this needs to go back 0 or negative 5 to 5. Or it could have hit cancel. I don't know. Thank you. I like to do things the hard way. And then, so I need to come down into here and change my t range here. Okay. So I'm going to go about 1.8 or so. So 0 to 1.8. And now I should be able to go much smaller. So I'm going to go 0.01 with that and hit enter. And now it seems to work. Now, again, I want to draw kind of a graph of this. So the zoom box would be a pretty good one to do. Zoom in doesn't work too bad. Zoom box is a little bit quicker. But, okay, so there's the picture they're looking for on number 6. Okay, so the thing goes up and then it kind of curves around and comes back down. All right. Now, I'm kind of jumping. Well, we'll go to we'll do number 9 when we get to that. So they now ask us. So let's go down to number 7 now. And this is the real important stuff, really, for this. 7 and 8 are really the calculus aspects of the motion in this particular problem. And number 7 says, find precisely by calculation the value of t at which y first stops increasing and starts decreasing. So what are you looking for there?
When the slope is 0.
What slope?
The slope of the path.
Okay, the slope of the path. The slope of the path is 0. Would when it stops going up and starts coming down, is what you're saying? Now, when is the slope of the path going to be 0? Well, that's a fraction. And when's a fraction ever 0? When the top is 0. So isn't it really when dy dt is 0? Isn't that what we're really interested in? Now, they're the same thing. But what I would really like to focus on here is it's the vertical velocity that we're talking about. Now, several people that I talked to last night about this fourth block mentioned, but he isn't really stopped. Is that true? Is he stopped at that point? Only in the vertical direction is he stopped. Right? Remember when we were doing the x-axis problems and we said, okay, if I'm moving to the right and then I turn around and come back to the left, what do I have to do first before I turn around? Stop. If you're driving in your car and you turn around, a lot of times do you ever really stop? You know, when you make a U-turn, you don't really stop, do you? However, your eastward, if you're going this way, your eastward direction would stop, right? If I'm going to the right and I turn around with a U-turn, at some point I'd quit going east and start to come back west, okay? I've still got some north-south going on, okay? But at some point, I stop going east and start to come back west. All right, so what that means here is that we want to know when y prime is 0. I guess the reason, Tyler, I would focus on y prime more than dy dx is this is an easier equation to work with, right? So you go back to number 2, which is where you have dy dt, and you just set that equal to 0. So we go onto our calculator, and what was the equation? Somebody tell me the equation for
0.3 plus 4 cosine of 2t.
0.3 plus
4 cosine of 2t.
4 cosine 2t. I want to set that equal to 0, comma, t. Now, what else did we say when we solve a cosine equation that we probably need to do? Limit the domain. Okay, whenever you solve a cosine sine type equation, you better limit the domain. So we're going to go to the vertical bar, and we're going to say 0 less than or equal to t less than or equal to what? Yeah, it was 1.5, 1.7. I mean, because we know it happens somewhere in there. That's what we just said on number 6. Okay? And since I have a decimal in there, it should give me a decimal answer, and there it is. Okay? So that's an answer you need to be able to find. But again, you've got to understand this thing we talked about with horizontal vertical velocity. Now, they tried to be honest, they helped you out pretty nicely the way they worded the question. They said, when does y stop increasing and start decreasing? I mean, forget parametric equations. That question right there just begs for y prime equals 0. Right? I mean, we've talked about that a lot. Right? Think of the chart. When y starts increasing and stops increasing, starts decreasing is when the derivative is 0. Okay? All right. So you do the derivative. The problem is you got so many x and y in different equations, you got to know which equation is which and what you're doing. Okay, so 0.822. Number 8 says what? Is he stopped or is he still moving? Justify your answer. So we already kind of answered that. He's still moving, but how would you justify that?
Because there's still a change in the line.
But you've got to do more than just say that. There's got to be a mathematical, there's got to be a number answer that justifies
Can
what.
you give the answer of his y prime? You give this horizontal. Oh, yeah.
It'd be x prime.
Yeah.
And do what? How would you find that? By doing what?
Find the derivative at that point.
At 0.822. So take that number. In other words, we just found that y prime is 0 at that point, which means he stopped going up. But by plugging that number into x prime, we find what?
Where did he start? How fast he's moving horizontally.
Okay. By plugging that number into x prime, we find his horizontal velocity. There it is right there, guys. X prime is horizontal velocity. By plugging a 0.822 into x prime, we get his horizontal velocity. We already know y prime will be 0 when we plug that in. That's what we just saw. He's not moving vertically. But take that number, so that's a good way to do that, and this is the easiest way to do that is with the vertical bar. So tell me what x prime was.
0.4 cosine of t.
Slower. 0.4 cosine of t.
Minus 0.4 t.
Minus 0.4 t, because this is the one we had to do the product rule on.
Times sine of t.
Good job remembering this multiplication sign.
And then what?
And then vertical bar.
Vertical bar. And then just grab that, because that's just what we need right there. Up arrow, down arrow, enter. Okay? That'll just grab that. That way it saves all the decimal place for us. Actually, we don't care about all the decimal places now, because all we really care about is what? If it's 0 or not. Is he moving in the x direction? So we don't really care necessarily, but it's positive, which means he's doing what?
Moving
To the right, because this is his horizontal velocity we just found. So by the fact it's positive means he's moving to the right and barely, right? Because it's almost 0. So he's almost stopped. And of course that would lead us to say in parametric motion, when is the particle stopped? Both have to be 0. We'll go back to this speed equation right here. When's it stop? When its speed is 0. The only time the speed equation can be 0 is when x prime and y prime are both 0. X prime and y prime both have to be 0. He's almost stopped, but he's moving just a little bit to the right. Number 9. Use the zoom box feature to zoom in on the point in problem 8. Does this confirm it? Okay, so we come back to our graph. Okay, let's do a zoom box on this corner. All right, and I'm going to keep doing it. Now, yours might not be rounded quite this much, but there's something else that I found on this. Now, if I go Control G, when I was first graphing this, I was running into a graph that was jagged. And yours might look like that as well. If I go back and look at the equation, since I have changed that t, 0 to 1.8, I was able to go 0.01 or smaller, a smaller number like this, then this made this look better. Okay, but that's because I went from 0 to 1.8. When I had this going 0 to 12 or in a bigger range, then it wouldn't let me get as small on the t-step. Now, what I want to do at this point is trace. Now, here's the other thing I found. If you go into menu, under trace, there's something here called the trace step. On the old calculators, the T-step and the trace step were the same. It's not true in this one. When I go into my trace, or excuse me, when I go into this equation line down here, this T-step used to also be the factor that it traced on. That's not true in this one. So the T-step here is just when it graphs. So it'll be smoother. The smaller you make that, the smoother it'll be. But what you have to do here is go into the trace step, and don't have it be automatic. Okay? Let's change that to 0.01. Trace step too large. Let's change it to 0.05. Trace step too large. Let's change it to 0.1.
You're going
You're
bigger.
going bigger.
Trace step too large.
You keep making it go bigger and it keeps saying it's too large.
That's right.
Let's try one.
Wait a minute.
How big can we make it before it's not too large?
I don't. Jeez. Okay, I'm going to type in, let's see this. Now this is interesting because this is not how it was working for me earlier. Okay, there's my trace. Okay, 0.84. Now let's go back to the left. Wow. Yeah, I can see why the trace step was too large before. You hated to have to get this done in less than half an hour. Well, we already found the value, right? What was it?
0.823.
0.822, what was it, 9 something? Okay. See, we found the value already. Now, that looks very much like a local max. And the local max, we always said, was a derivative of 0. Of course, we didn't have to be so specific back then because we had a y equation in terms of x, and so our y prime was dy dx, and we didn't have to worry about with respect to and so forth. But here we got to be really careful, especially with the y. Because when we say y prime, which y prime are we talking about? Are we talking about dy dx? Are we talking about dy dt? They're two different things. That's the Leibniz notation is very important there. Now, it turns out that they're both 0 at this point, right? Y prime is 0, whether it's the slope of the path or it's the vertical speed of the particle, and that's always going to be true in a local max on a path. The local max on a path, it quits going up, starts coming down, the slope is 0. The y speed, the vertical speed, is also 0. Okay, so that's going to be the same. Now, so they ask, is 0.822, does that seem reasonable? And yes, it does. So by zooming in, it looks like, yes, it has stopped going up and is starting to come down. But it is still moving to the right. But slowly, because it's about to quit moving to the right. Now, let's finish this up with one last comment. Here's the slope of the path. Okay, let's do it up here for a recorded audience at home. Right here, we just said the slope of the path is 0 when the top is 0. That means when its vertical speed is 0. What happens if its horizontal speed is 0?
And it's going straight off.
Then it's undefined. That means it's not going this way, but it might be going this way, right? You would have a vertical tangent, and a vertical tangent, of course, the slope is undefined. And so the formula makes sense there as well. If x prime is 0, then that's in the bottom. The slope has to be undefined. Therefore, that means that it's a vertical tangent. Okay? All right. That's about it. That's about all I can tell you on those. All right. Get your calculators out. Those handful of you that actually have your calculators.
Is not one of them.
And let's go. Let's change. Let's change. We need a presenter here. David's always a good presenter. I like it when he presents.
No. No. It's so bad at this.
That's what makes it fun for everyone else.
Oh, come on.
Oh, whoops.
Whoa, Harry.
Yeah, pick Harry, pick Harry. It looks cool, dude.
Hey, awesome.
I changed my T to 50.
Oh, to have it keep going?
Yeah.
Oh, cool. Good idea. All right, David, you're on.
What am I supposed to do?
Okay, go Control G. Go into the equation part.
You want to change the whole thing?
Yeah, I want to change the whole thing. Okay, so I want you to put in x equals t. Okay, and if you want to play along with him, that's great. Or if you want to write any of this down, we might jot down a few of these equations as well.
Like x of t equals t?
Yes.
Okay.
Okay. Now, sometimes when we do these equations, we don't always write x of t. All right, when we do parametric equations, a lot of times we'll write x equals t. And I want to write y equals t squared then. Okay? Now, before you hit enter or change the t step or anything, I want you to think about a prediction of what this graph will look like. Is there, I mean, just look at those two things on the board, or the two things that he has typed in. Anybody have a thought about what this will be?
Does it will go? Yeah, would it be like a parabola?
Absolutely. Why?
Or if x is t, that means that your time is on the x-axis, just like normal.
If x and t are the same thing, and our parametric graph has x down here and y up here, but if x and t are the same, then t is just like here. Isn't it really just as simple as a substitution? If x is equal to t, then wouldn't it be true to take those two and combine them and end up with y equals x squared? That's exactly right. That is called eliminating the parameter. And it's something that it's easy in some problems and it's hard in others. But if you can do it, it turns a parametric graph into a normal function graph. Now, think about Adam Ant. That one's not going to be easy to do. Okay, number one, it's not a function, right? It fails a vertical line test all over the place. So it's not going to have a nice, easy function name. It's just not going to. But these simple ones, it's pretty easy. And it is as easy as a substitution. If x is equals t, then that means I can come down to this equation and put an x in place of t, and there we go. So I'm going to get a parabola. So go ahead and change the t step. Let's have the t step. Since t is basically the x, leave the t step, let's make it 0 to 4. And leave your t step at 0.01 if you want. I don't think it'll let it stay there, but go ahead and hit enter. Now we're going to have to change our window. Let's do a zoom standard. That should be easy enough. Now, okay, we got parabola, sort of. What happened?
Your t stuff doesn't have less than 0.
Well, but I mean, not the t step, the t range. Yeah, the t range. In other words, we said 0 to 4 for t. Well, if t is x, then that means you're only going to plot x's from 0 to 4. So go back into the t range, and let's do -4 to 4 this time. Now, usually in the problems we've done so far with parametric, we've started t at 0. Well, that's because it was time. T was time, and so that made sense for t to always start 0. But now our t could go -4 to 4. Now, if we would scroll up there a little bit farther, we would see that the parabola actually stops. Unlike a function graph, it'll just graph forever and ever. But if we could go ahead and grab, see what he did? He clicked and held there, and he's got the hand, and he can drag it down. Or you could just go into your window and set a bigger Y, but if we keep going, how far do we have to go? To where?
16.
There you go. Far enough, 16, right? Because 4 squared is 16. So it actually stops, okay? Because we only told it from -4 to 4. But we do get the parabola. All right, now, go ahead and You scroll it back up to where we can see the bottom part of it. And now I want to trace. So let's go ahead to trace. And let's trace at, well, let's just trace around a little bit. Arrow to the left.
Really small.
Oh, we're still on that really small. Go to your trace step. Trace step. Change it to 0.1. Think it would be too large? I don't know.
Oops, I missed the point. Okay, okay. Got it.
Okay.
I do that.
Yeah. All right. So
What the?
just hold down the left arrow. Does it keep moving? Okay. All right. All right, so go ahead and stop there. So we get some values. Now hold down the right arrow. Let's just hold down the right arrow. Let's watch it move. Let's watch the point move here. Okay, especially down in this region. Let's watch it move. Okay, it seems to slow down, right? And then kind of speed up. Okay, now stop. Why is it doing that? Why is it speeding up then? Why does it kind of slow down there? And
Because it goes farther on the Y.
the points are getting closer together. This would get into horizontal vertical velocity, right? Especially its y velocity is getting bigger as it goes up. Because what would its vertical velocity be? Well, it'd be y prime. Its vertical velocity would be the derivative of this, which would be what? 2t. So as t gets bigger, as time goes on, the vertical velocity gets faster and faster, and it's moving up. Okay, what would its horizontal? Now this is important. Now listen. Now, what's its horizontal velocity?
Or 1.
It'd be the derivative of this, right? Which would be 1. So as he held down the right arrow and was moving along with t was going at a constant rate, right? Or it's horizontally, excuse me, the x, which is the same as t here, is going at a constant rate. But the y was changing because it was getting steadily faster and faster. Okay, so now I want you to go in and change the equation again. This time we're going to change it to x equals t cubed and y equals t to the 6th. Now, before you hit enter, say it again. Did you say it, Eric?
Yeah, I said it was going to be the same.
Why?
Because the relationship is still the same.
Think about substitution again, right? Isn't t to the 6th the same thing as t cubed squared, right? And t cubed is equal to x. Sometimes you have to be creative in eliminating the parameter. Now, eliminating the parameter, what I'm saying is let's combine the x and y equations into one equation that's y equals something with x. So we get y equals, since x and t cubed are the same, I can make a substitution and I get the same thing. So, go ahead and hit enter.
So you would take the cube root and then plug that
It-
in for
Okay, now Tyler said something interesting, because one of the things on our next quiz I'm probably going to ask you to do is eliminate the parameter. Here's a parametric equation. Eliminate the parameter and write it as a single equation. Well, one of the ways of doing that is take the x equation and solve for t. Instead of, maybe you didn't see this, you could have solved for t by doing the cube root. Get what t equals. If you get what t, it's just two equations to unknowns, right? If you get what t equals in this one, then you can substitute into this. Well, if you do the cube root of x, which is x to the 1/3. If you do x to the 1/3 to the 6, that's x squared. So that would be a way you could do it as well. Same picture. Now this is where the thing comes in about slope versus speed. Same path is what we're saying. These two parametric equations have the same path. Let's trace. Go over to, just trace and type in -3. Or, yeah, just type -3. Oh, that's bad.
Hit Control Z.
Control Z will undo that. Control Z. Controls, okay, perfect. All right, we'll just stay right there. All right, now, hold it. Are you in trace? You're in trace. Hold down the right arrow now. Now watch it move. Now, stop. What do you notice so far as it was moving? Arrow back, arrow back.
it would really fast.
Wasn't it moving faster than it was before?
Yeah.
I think it was moving faster than it was before in this area. Okay, go ahead and hit the right arrow. Do it again. Okay, now watch it through here. To me, it was slower through there. Okay? But again, that has to do with this, because what would be the y prime in this problem? 6t to the 5th. Here the y prime was 2t, right? So it's going to grow much, much faster, especially when you get outside of 1. But when you get numbers less than 1, you take 1/2 to the 5th, 1/4 to the 5th, then those get to be really small numbers. So when you get down here inside of -1 and 1, the velocity is actually going to be much slower. When you get outside of -1 to 1, the velocity is going to be much faster. Two different particles on the same path is what we have here. We got two parametric equations, so those are two different particles with different horizontal and vertical velocities, different speeds, same slopes. Right? And again, it comes back to that having that same relationship. They're going to have this, it's the same path. Okay? Now, at different times, they may have different slopes. Okay? But same path. In your book, if you want to get your books out, wouldn't be a bad idea at this point. There is a picture of this on page 244. Page 244. Uh-oh, that's bad.
Oh man.
Take a picture of
You
them.
could just,
How many levels of undo do I have on this?
you could just erase what's on the board.
Yeah, you could just use the eraser on what's on the board right now.
No, it'll erase what's.
Oh, yeah, well.
It'll erase.
It doesn't like detect.
Shoot.
Yeah.
It doesn't detect the marker particles.
But you know what? This is I think that's okay. I'd save this. Thank goodness. All right.
That's
There's still a lot of ways he could go with this. I mean, it looks all right so far, but I'm not. No. Okay, all right. No, David, there's still.
There is. There's push bars too.
Oh, yeah, because the thing.
There's even one that looks. There's even a book.
the exclamation mark totally means something bad.
All right. Page 244 at the bottom. It shows pictures of what we're talking about. The points on that picture are at the same t-values. Okay? Again, think of time. There's one at -1, at 0.75, at -0.5, at 0, at 0.5, and so forth. And so notice how when they're further apart, that tells you the particles what? When the points are further apart, the particles what? Moving faster. When the particles are close together, moving slower. Okay? In a parametric graph. So again, the parabola is just the path, the sidewalk that it's moving on. Okay? But the points are where it is at certain times. So comparing equal t-values, you can see that the one on the right is actually the first one we did. Okay, the one on the right is the first one, more evenly spaced, a little more constant velocity, or closer to being constant velocity. And the one in between is what we talked about. It's faster outside of 1 and -1, but slower in there. Okay, because the speeds were different. And the horizontal vertical velocities were different. So important to understand how those things work together. Okay, so eliminating the parameter, we're going to do that on, Tyler said something really important. Some of the homework questions, they give you some linear scenarios. Okay, a linear parametric equation simply is this. If I have 2 plus 3t, if that's a line, and I got y equals t minus 7, if that's a line, that is going to make a line. That is going to actually be a line segment based on what t range you set. If I want you to eliminate the parameter on this, the simplest way is to solve the first equation for t. Let's go ahead and do it. Why don't you go ahead and jot this down just so you've been through one when it comes to the homework. If I give you this parametric equation, and it is a rule that if both x and y equations are linear, then the path will be linear. Okay? It's not true that if both x and y equations are sine, that the path will be sine. Okay? I mean, we saw that in the Adam Ant. We had a sine and a cosine, and it was all over the place. But if I take this and I solve the first equation for t, okay? And if I was doing it, I would divide by 3 this way, 1/3 x minus 2/3. I would divide by 3 like that. Then I would substitute that into the second equation. So I would have t, which is now 1/3 x minus 2/3 minus 7. So this would be y equals 1/3 x minus 7 2/3. That would be eliminating the parameter. That would be the path. This line would be the same as this line if I graphed them. The difference in doing it in parametric is because I can make it just a line segment. I can look at just one piece of the path by setting my t range. Okay? Now, you're not always going to be able to do this on problems because you're going to get ones where you can't solve this one for t, and so you can't eliminate it. All right. I want to touch on another neat use of parametric equations. This is probably not going to be on our next quiz, but it is something that shows up on the AP test. It's something that you can use on the AP test. You don't have to. There's other ways to do it on the AP test, but not as easy as parametric. The problem is remembering that you can use parametric. Okay? So, the example I want to give you is this. And David, we're going to let you do this for us again. Right? I want to put into your graph, I want you to put x equals t. And y equals sine of t. Now, while he's doing that, what do you predict this will look like? In the regular sine curve? Again, whenever you have x equals t, that's the easiest situation you could have, because x and t are the same thing is what that's saying, so we can substitute an x right there. We get y equals sine x. This is going to be the graph of y equals sine x. So what would be a reasonable t range? 0 to 2 pi would be a nice t range to set. Matter of fact, understanding that when you have a parametric equation in front of you helps you, instead of just guessing what a t range should be, this gives you something to try. So go ahead and hit enter on that, and Windows not bad. And there it is, the sine graph from 0 to 2 pi. Now, big deal. Why would we want to do that to do the sine graph? We wouldn't. Where we would use this is for inverses. Now, we just got done talking about inverse functions when we were dealing with arc sine and arc cosine and those at the end of chapter 3. What is the one thing, or one of the things, that is true that you do to make an inverse of a function? If I gave you y equals x squared and said, I want you to write the inverse of that function, where do you start?
You switch y and x.
Interchange the x and the y. Wasn't that really easy to do right here with a parametric equation? Since you have a separate equation for the x and the y, what should the inverse be? No. Interchange the x and the y.
Y equals tx
Well, we always want to write x first. So x equals sine t, and y equals, how much easier could that be? That's going to be the inverse. You interchange the x and the y coordinates. David, do it. So if you want to do so if you want to graph a sine curve, one way to do it, graph any curve, let x equal t, and then let y equal sine t. That's the sine x curve. You want to graph x squared? We just did it. X equals t, y equals t squared. That'll graph any regular function for you. You want the inverse of it? Just switch the x and the y. Look what you get. Which you could never get in function mode, but you get the inverse of it. Okay? And now you could do things like trace, and where this comes in handy then is, you'll see later on when we get to the AP test. My challenge to you then in March when we're practicing this and we get a problem with inverse functions, I'll say, hey, we could use parametric equations. Remember how? And we'll give bonus points to anybody who remember. Well, maybe. We'll see. But what we'll say is, oh yeah, you let x equal t like this, and then you flip it, you interchange it, and then you get this. And then you can trace, and you can find some of the, especially in the multiple choice questions where this comes up, and you can get, by tracing and stuff, you can find what? You can find some. This is recording, I think. It records this. There you go. Okay.
Leave it there for a while.
Oh no, it's the key press history. That's what I can do. Oh no, it says start recording. Let me. Oh no. I don't know what happened. My computer's going slow enough right now. I don't want to
Just be like double recording it.
No, yeah, exactly. All right. So yeah, that's right. I'm recording the screen. Perfect. All right.
Yes.
So on and we'll get this in. All right.
Okay.
Yeah.
Page 247, please. Page 247.
Right.
What are you, 12?
I should say that speaking of first, that might be in 15 years of calculus the first time I've heard that in class. Might be one of the long list of many firsts from this year's calculus class. All right. So many of them courtesy of Dave. All right. Example 10. Please take a look at this because several of your homework problems, and they're ones towards the end, which I know as I come around and look at homework, the ones towards the end sometimes, well, anyway. So example 10 talks about a pitcher throwing a fastball, and it says when and what speed does the ball cross the plate? Is it a strike? And if the batter, catcher, and umpire all miss the ball, where does it land? So, two-dimensional motion. They give us several scenarios here. Now, one of the things that's a little bit confusing in this problem is they use F and G. Now, you have to notice in their solution that they let X equal F and they let Y equal G. I'm going to go ahead and just use X and Y, not to confuse the issue. So they go through and list several things we know. Okay? Now, they tell us that in example 10 here, they tell us that the ball starts from the pitcher's hand at initial height of 7 feet. Now, using these notations over here on the board, what would that be? That the ball starts at an initial height of 7 feet.
It would be in the Y.
That would be the vertical position. Come on now, pay attention to this, guys, because this is important. This stuff with the notation is critical. We're really getting into almost kind of an initial value problem here. Okay? And what we set up here is going to be used in several of the homework problems that you have today. All right, so it's launched from a height of 7 feet. So it's vertical position, and that's what I wrote up here about y, is a vertical position. Okay, so we know y of 0 is 7. We also know that, what else does it tell us? We're going to ignore wind resistance, which is kind of silly when you're throwing a baseball, but anyway, that makes it a little more complicated, so we're going to ignore that. It's got an initial speed of 150 feet per second. Okay? And notice what it says in the first sentence of example 10, traveling what direction? When it leaves his hand, he's throwing it exactly horizontal. Now, I'm not sure that's always true when a pitcher releases the ball, but to simplify things, we're going to do that. So it leaves his hand horizontally at an initial speed of 150 feet per second. What's that up here? That's x prime. So we know x prime of 0 is 150. Okay?
We also know y' 0 is 0.
We would also know that it has no vertical velocity when it leaves his hand, because it's traveling only horizontally. We know that the pitcher is 60.5 feet away from home plate. Okay? So we're going to call, let's call the pitcher's position when it leaves his hand, let's call its horizontal position as 0. In other words, as we think about a picture of this scenario, when it leaves the pitcher's hand, let's let that be right on the y-axis. Let that be an x of 0. And then the ball is going to, follow some sort of path like this. Now, it's parabolic. Any object in free fall is either going to be moving straight up and down, or if it's two-dimensional motion, is going to be in a parabolic shape. Okay? It's always in a parabola. So some sort of a parabolic shape as it leaves his hand. Okay? So we would know x of 0 is what? That's the horizontal position. X is the horizontal position, and so at time 0, we're calling that x is 0. So these two together give us this point 0, 7. Remember, in here is t, time, right? Inside here is time. So horizontal velocity is 150, vertical velocity is that. Okay, now what about acceleration? Once it leaves his hand, remember second derivative is acceleration? Once it leaves his hand, what force is pushing it horizontally? Nothing, right? What would be pushing against it horizontally? Air resistance, friction, but we're ignoring wind resistance. So the acceleration horizontally of the ball would be 0. There is no horizontal forces on the ball since we're ignoring wind resistance. So the Metrodome evidently is a vacuum, I guess, or wherever he's throwing it. Y double prime of 0, which would be the vertical forces of acceleration on the ball, are what? Negative, are we using feet or we're in feet here, so negative 32. We failed in changing the United States to the metric system back in the, well, when I was when I was your age, 1980. They tried.
Yeah.
And they failed. You notice on like the water bottles? Right? This is when this happened, starting in like 1980. It says 1.05 pints, 500 milliliters, 16.9 ounces, right? They always used to say ounces. They started doing that. The state track meet in 1979, you ran the mile, you ran the 2 mile, you ran the 880, you ran the 440, right? 440 yards, 880 yards, right? 1980, the first year of the state track meet was in meters, 400 meters, 1,600 meters, right? We don't run the mile, we run 1,600 meters, which is actually short of a mile, right? That was part of it. Congress had decreed that we were going to change to the metric system. Never made it. Never made it. The cars have, in the speedometers, right, still have kilometers per hour on them and miles per hour. That's when all that stuff started as part of the transition. Some of it's still hanging around, but anyway. So we're in feet. Negative 32. Those are all things we know about this scenario. Now, they go ahead and give you, if you turn over the page, they give you the equation for x of t and y of t. Now, one of your homework questions is going to ask you to show where those came from. Now, we've actually done this before. They come from this right here. Now, essentially, these are differential equations. Matter of fact, let me change something here. I wrote something in, well, it's not incorrect, but I could do better. Right there. The acceleration, the forces on the ball horizontally and the forces on the ball vertically, are they at the beginning?
Yes.
Yes, but they're always the same. There's never going to be any horizontal force if we ignore wear resistance, and gravity is going to pull on the ball throughout the entire time. So this is, those equations are actually that for all t. So how could we go from x double prime and get an equation for x? Antiderivative. What's the antiderivative of 0? Any constant. Okay? So x prime would be just some constant, c. Well, it turns out that x prime is 150. Now, if the ball leaves his hand going 150 feet per second, and we're ignoring wind resistance, what's the ball's horizontal velocity going to be? Always 150, right? So what that's telling us, so you see how you use antiderivatives, that'll be 150, and then you do the antiderivative again to get x. So you can see how we're going to get that. That'll be part of your homework. But if you look on page 248, they tell you that x is equal to 150t. Well, again, that makes sense. If one antiderivative is a constant, which we know because of they told us it's 150, then we do the antiderivative again, it's going to be 150t plus 7, but we know that x of 0, or plus 7, plus c, and we know x of 0, 0, that tells us the c. So it makes sense where that equation came from. The second equation they give us is 7 minus 16t squared. Okay, we'll think about that a minute. Practically doing this, we're doing this problem together, right? We're working together here. What's the antiderivative of y double prime? It'd be y prime. What's the antiderivative of negative 32? Negative 32t plus c. What c? It'd be your x prime, no, your y prime of 0, 0. So that'd be negative 32t. That's y prime. What's y then? Negative 16t squared plus c. What's the c? Oh, the initial y value. Initial y value set. Okay. So anyway, they give us then this, which is the parametric path of that ball. All right. So, David, graph it. Okay. Yes. Okay. So, a couple of your homework problems. One of your homework problems is going to take this problem and change one of the parameters, one of the variables here, the initial velocity or something. So it's going to work very much the same. Another one of the problems is going to give you new equations that include wind resistance. They're a little more complex, but they go ahead and give those to you. Okay? All right. So we go ahead and graph this.
Yeah, what do I use for the t?
Make sure that's t squared there on the 7 by 16. And, okay, t is time in this problem, so how long is it going to take the ball to get to home plate? Wouldn't take very long, right? So let's go 0 to 1 and see what we get. 0.04, probably good. Okay? Now, how far is it to home plate? 60. So watch it. Let's go ahead and set your X max. The Y looks good there. Let's go ahead and just change your X max in your window settings to about 80 or so. You can do fit, that's fine. Just change your X max to 80 maybe. Because remember, at one point they wanted to know where the ball would hit the ground. Okay? Now, we can't see where it hit the ground, but that's okay. One of the questions was, what's the speed when it crosses a plate? One of the questions was, is it a strike? Okay? So, which one of those do you think would be easiest to do? The speed when it crosses the plate? Or how would we tell if it's a strike? The y, which would be this one, this equation, at the time it crosses the plate, right? So how do we find that time? Because remember, when you trace, what value do you trace with? T. See, we can't trace when x is 60.5. Isn't that when it's going to cross the plate, when x is 60.5? So you really got to think about what the different things stand for. Horizontal position is x, and so at the plate it's 60.5. So you could start tracing now and guess, but we're going to obviously have to do more than that.
Could you put 60.5
Yeah.
in for x of t?
Set it equal. That's what we're going to do. Right. So right here he's pretty close, right? And look at the height. What is it? 4.4. Now what did they say about the strike zone? I think they said something there. Maybe they did. Okay, 4.4 feet. Well, the strike zone is, supposed to be from the knees to the chest, somewhere in there. So 4.4 feet might be close. A little high, probably, but it's pretty close. This is probably 3 feet. Pretty close. Depends who it is, right? Depends on the batter. But is it a strike? So that seems reasonable. But how would we find that time when it crosses the plate? Because then we also want the speed, right? And the speed now is going to be this equation. But we got to know a certain time. We got to find the x prime at that point and the y prime at that point. So what is the t value? Tyler said a minute ago, but what are we going to find? When did it cross the plate? When x is 60.5. So right here, when this equation, 150t equals 60.5. There you go. That's easy. Just go to your calculator part and divide that. Okay? So it's going to cross the plate. When t equals what? 403. Okay, about half a second or so. Now we want to know the height. How exactly? We would do what? How high was it when it crossed the plate? Plug that into what? The y equation, because y is the vertical position of the object. So, and again, I want you to show this work. Put on your paper y of 0.403. That way, if you screw it up when you type it in, at least you can, you're showing that you're knowing where to plug it in, and that's worth some points. So you go ahead and do that on your calculator. 4.397. Okay, which, like we said, is close to being a strike. And then it wanted to know the speed. So what do we need for the speed? We need x prime and y prime. We got to plug in this t value, and then we do the square root of all that added together. So what's x prime? We got it right here. X prime is 150. Y prime is negative 32t, right? So the speed is x prime squared, don't even need to plug in anything, plus, and then negative 32 times 0.403. Make sure you use an unrounded 0.403. Make sure you use more decimal places than just that. Okay? There'd be your speed. Okay, that's how we would, there's a problem where we would use about everything in here. We didn't use the slope of the path for anything, but the speed and those various things we did. And according to their answer here, according to them, on page 248, they said it was going 150.55 feet per second. It was going faster when it crossed the plate than when it left his hand. Because we're ignoring wind resistance, right? We already said if you ignore wind resistance, then the horizontal speed is going to stay the same. And it's dropping. Gravity's pulling it down, so that's speeding it up a little bit. And so that makes sense. All right. A little hard to throw a curveball, probably, if you're ignoring wind resistance. All right. So, Okay? Question about that? I mean, that takes into account those various things. And using what we learned about differential equations, we should have been able to take that information, go all the way to build those two equations, really by antiderivatives, using initial conditions, but they gave them to us, and then we get to that answer there. All right. What was the other one? Oh, where does it land? How would you find out where it lands? Devin, y equals, you would set y equal to 0 because that's when it hits the ground. When its vertical position is 0. So we would take this equation, set it equal to 0. But that would give us the, what? That wouldn't answer it totally.
That would give you the time.
That would give us the time that it hits the ground. But they want to know where it lands.
Take that time.
Substitute that back into the x equation. So you take that times 150. Right? See how, if you understand what the different equations stand for, then it's easy to know which one to do. Okay, the most common question I get from people is, what do I plug in and where, and I got to set this like you're trying to memorize something. It's not about memorizing, it's just about understanding the x equation is its horizontal position, the y equation is its vertical position. I want to know when it hits the ground, that's when its vertical position is 0. So you set the y equation equal to 0 and you solve it, but that's t. Oh, because that's a time when it hits the ground. I want to know where it was when it hit the ground. In other words, I want to know its horizontal position. That's x. So I take the x equation, I plug t into that, that gives me what x is when it hits the ground. Okay, so these things all work together. All right, your homework for tomorrow. And adjust it here a little bit because I'm not going to take time to work through the one in there I said I would. So we'll take off number 12 from the homework assignment. Okay, the one that I said I would do in class. Okay, we got about 15 minutes here. I want you to use that time, please. We start in the homework on problems 1, 2, and 3 with some basic graphing. Let me summarize a little bit because this is probably our last day on parametrics until we may come back and review them later. Let me just review the things I want to make sure you can do on parametrics. You need to be able to go in and graph them. Right? David's got that handled. You got to be able to go in and graph them and trace, be able to set your trace step and stuff, be able to trace and zoom in and so forth on one. That's what questions 1, 2, and 3 are about. Okay? You need to be able to work with these equations like we just did, these 3 things here, and you might need to be able to eliminate the parameter on some simple ones. Okay? Now, and that's what I think problem 6 is about. Okay, this is 4.4 now we're on. Okay, so on that homework line, you're down on 4.4. Okay, those are the things that I need you to be able to do it. And when I talk about graph them and trace, also it talks about sketch it on your paper and write the direction of travel. So put just little arrows, on it that show kind of the direction of travel of the particle. Okay, you can get that by just tracing. Just hold down the button to the right a little bit and see which way it's going around the thing. And it also asks you to put points on there at t equals -1, t equals 0, and t equals 1. So trace at those points and then put dots on the graph at those points. Okay? There will be a question on the next quiz very much like that. Here's a parametric equation, sketch it, mark the direction of travel, plot these points. Okay, go ahead and go to work.
Do you happen to have an extra one of those?
These?
Yeah.
I do.
Yes. Yeah.
You want to sign the board now?
Here. She made
Well,
Just battled one during the entire break.
My dad did, so it's okay. Thanks.
I won't grab. But hey, all I look at it as a friend.